that's above here, which as you can see is wet and soft.
In terms of use potential, this soil is a good example of the distinction we must draw between total soil depth, that is the depth of material formed by pedologic processes, and the usable depth, sometimes called effective depth. The total soil here is quite deep, but the usable depth, in terms of rooting depth, is very shallow. The E horizon is a severe barrier to roots. It is leached of all nutrients and is often waterlogged during the wet season. In the dry season, the particle size distribution of the E horizon is such that it sets very hard. None of these features are likely to encourage roots, and so rooting depth for most plants is limited to the shallow orthic A horizon. Even this will be very wet during times of heavy rain. Agriculturally then, this soil is of low potential with severe depth and wetness constraints. Similar problems surround its use as a building area, and effective drainage or waterproofing mechanisms would have to be installed.
We're now moving down the slope from that longlands profile, which we called lower mid-slope, and now about where I'm standing is getting very close to the centre of this small wetland area that we have here, which is picked up very nicely by the change of the grasses at this time of year. So a look at the vegetation would give some indication, I'm sure, that we could expect the soils here to be much wetter. And if we look at this particular profile, which is a catsprate soil form, there are certain features in it which we find very commonly in these wetland areas. The sort of features that we want to look at here, if we start at the top, what you notice immediately, I think, is that there's a lot of roots, which we didn't really see in the other longlands pit. And very importantly, the size of these roots. They're very thick. They're not your average grass roots, which are much thinner. So these roots are the roots of these water-loving grasses which only grow in this wetland area of the plateau. You will also see that the roots peter out. They come virtually to a stop at about this sort of level here, whereas we'll see the soil is getting much wetter and much heavier in texture, and therefore much wetter. So the catsprate soil form consists of an orthic topsoil overlying this very heavy grey clay. If you're in any doubt that this is clay, it smears very, very easily. So this is a very heavy clay, and even now still very wet, even after the side of the pit has been exposed for a while. And that's the main reason why roots, of course, won't grow into this. It's just too wet and too heavy all the year round. So these grey colours that we see here are almost the diametric opposite of the red colours that we saw up the slope. Red colours equals good drainage, grey colours extremely poor drainage or permanently waterlogged. If we look again at the top, you can see again, especially maybe on this face here, these orangey streaky mottles. So again, as in the longlands, only much more clearly expressed here, this is what happens when the topsoil dries out during the drier parts of the year. The air is able to get in through the root channels, and the iron along the root channels reoxidizes to these orangey streaks. In the very wet periods when the water is essentially at the surface here, this iron will revert back to its grey colour, which is reflected in the G underneath. So these streaky mottles are an indication of this alternating water table, alternating oxidizing, reducing conditions. Okay, so now we have to think about what the parent material of this particular soil might be. We're down in the wetland near the bottom of the slope. We've seen upslope that the dolerite especially is in movement across this slope by colluvial action. The boulders are rolling down the slope. And here, as luck would have it, in the bottom of the pit is another one of these dolerite boulders. Now whether this reflects a movement of dolerite down the slope to the bottom, or whether the dolerite is actually the parent rock here in situ, we know, for instance, that the next profile we'll look at, the dolerite certainly is in situ. There is no shale underneath here. So it's possible that here too the dolerite is the parent rock. But whether it's the parent rock or whether it's been added in by colluvium probably doesn't matter too much, because it's still the major driver in terms of parent material here, not shale. There's no evidence of shale in this pit at all. One feature of dolerite that we haven't mentioned up to now is the way that it weathers. It's a very, very hard rock physically, but quite soft chemically, because it's an igneous rock and therefore is particularly susceptible to chemical breakdown. And it weathers a bit like an onion, so that the dolerite weathers a skin at a time. And just here you can see from the boulder just a couple of pieces of the skin, the outer layer, in other words, of this particular boulder that are beginning to weather off, to break off. And as the dolerite weathers, it produces very clayey soils. So a lot of the material in the dolerite breaks down to clay, and that's one reason why there is so much clay in the subsoil of this catsbrate soil form. Okay, in this view you can see where we've come from. The misper at the top, coming down the hill to the oak leaf, was about a distance of 20 metres. Then between the oak leaf and the longlands was a distance of about 40 metres. Then from the lower mid-slope position of the longlands, as we come across to the catsbrate, as we come down that section of the slope, you may be able to pick out the change in the grasses, the change in the vegetation, as we go from an area which is somewhat drier on the lower mid-slope to an area which is almost permanently wet at the catsbrate, and the distance between those two pits is about 35 metres.
Clearly the main constraint to use here is too much water. One way to alleviate this is to install drains to remove the excess water, but this would effectively dry up what is in fact a small wetland. In general, wetlands play a number of vital roles within ecosystems, and draining them is often not sensible. Another method to get around the water problem is to ridge the soil so as to increase the usable depth. And indeed a similar technique could be applied to the longlands soil. Catsbrate soils are often used for pasture, with the animals being removed during the wettest parts of the year to prevent degrading the soil by compaction.
As we leave the catsbrate, we move across this small wetland that's here to another soil type. This is the Rensburg soil form, with again a distance between the two of about 35 metres. Okay, this is the Rensburg soil form, and at first glance it looks rather similar to the catsbrate that we've just come from. But closer examination reveals certain very important differences. But if we concentrate on just looking at the soil itself to start with, this soil has a much, much deeper topsoil than the catsbrate. This is the Vertic A horizon. It extends from the surface down to somewhere in the region of 60-65 centimetres probably. So a very much deeper topsoil than the catsbrate. The characteristics of the Vertic topsoil are a very high content of 2-to-1 shrink swell clays, especially montmorillonite. The clay which shrinks in the dry season swells in the wet season. This shrinking and swelling gives these Vertic soils very particular properties which we can talk about in a minute. Below the Vertic topsoil, coming in at about 65-70 centimetres or so, is a very similar subsoil, a G horizon that we saw in the cut sprate. It's greyish in colour and extraordinarily wet for most of the year. We're still in the wetland here, so obviously it's still very wet. And the Vertic A, in the same way that the cut sprate orthic topsoil, is showing these thick roots typical of grasses which can withstand these very wet conditions for pretty much all the year. And similarly as with the cut sprate, the roots pretty well stop about 40-45 centimetres down as the soil gets wetter and gets heavier, more and more montmorillonitic clay. A feature of montmorillonite is it shrink-swell, and as it shrinks and swells it can shear roots. So if roots get too deep into this sort of material, as the montmorillonite swells up and then shrinks in the following dry season, the roots get sheared off and clearly die. So the roots are pretty much restricted here to the top 40-45 centimetres or so of the profile. Other features of soils that contain a lot of montmorillonite are what are called slicken sides and cracking. If we take slicken sides first, slicken sides are what happens as the soil swells up and the parts of the soil push together as the clays gain water, and they push together and twist as they expand, and then in the dry season they'll move apart again. So you can see these features, they're very bright, shiny, pressed faces of clay as the soil masses move against one another. And there are reasonable examples in this particular profile. One effect of this shrinking and swelling that forms these bright, shiny faces that we call slicken sides, as the clay presses against one another, you can perhaps see that this forms a sort of corrugated surface. And in the corrugations, the roots get trapped as the soil swells. So the roots get severely flattened, and in extreme cases, as I said, they can actually be sheared off. The other feature I mentioned is cracks. In the dry season, as the soil shrinks, as the montmorillonite loses water, so it cracks. And you can see examples here, even though we're nearly in the middle of summer, we've had a very dry period, and so the cracks are still visible. And they run from deep in the subsoil usually right through to the surface and can get very wide in a very strongly Vertic topsoil. The face here, as you can see, is severely cracked, and it's very easy to pull blocks away, and that happens naturally when the soil is exposed. So these Vertic topsoils have tremendous difficulty standing up straight, which means they are highly erodible in an exposed face. Yet another feature which is rather peculiar to Vertic soils is their ability to what's called self-mulch. And it's again a function of the presence of these 2-to-1 shrink-swell montmorillonitic clays. The montmorillonitic clays, as they shrink and swell at the surface, break the soil down to quite a nice fine tilth, a nice fine seed bed. And you can see the beginnings of that on the top here, where you can scrape the surface away and you can see a very fine, finely structured material. This is the self-mulching properties that these soils have. So despite the fact they go very hard when they're dry, the surface is actually quite soft.
If you consider the damage that we talked about at the MISPA profile caused by montmorillonitic clays in the shale, then areas of Vertic soils can be considered as an engineer's worst nightmare. Very special building techniques have to be employed, to ensure that structures do not crack as the soil clays expand and contract. There have indeed been a number of very expensive engineering mistakes made as a result of not recognising the presence of Vertic materials. So, if not nice soils from an engineering perspective, what can we use them for? They are very strongly structured, highly fertile due to their low-lying position, and in this particular case, dolerite parent material, and are underlain by a permanently wet G horizon. We therefore should consider crops that enjoy wet conditions. In many parts of the world, these types of soils are intensively used for growing paddy rice. It is often relatively easy to flood these soils because they are often in the lowest parts of the landscape, near to rivers. Once fully wet, the Vertic topsoil swells and seals, so preventing any more water from infiltrating. Further addition of water then builds up on the surface, so forming the paddy. In the United States, these types of soils are known as black cotton soils, because some of the most productive cotton lands in the southern United States are on these soils. In northern KwaZulu-Natal and in Swaziland too, these Vertic soils are intensively used for cotton growing. Just as an aside, where Vertic material occurs in large amounts, it is mined and used to build cricket pitches. This Vertic soil and the red oak leaf that we saw upslope are almost complete opposites in their properties. The Rensburg is structurally very difficult to manage since it is often too wet or too dry, but is very fertile. The oak leaf is structurally perfect with free drainage, but relatively nutrient poor.
So as we leave the Rensburg pit, we actually walk uphill slightly to the next and last pit in this particular sequence across the saucer. So we've come out of the wetland, back up to somewhat drier country, as is indicated by again the change in the grass species. This soil is a Bonheim soil form, although again at first glance it might look very similar to the Rensburg we've just come from, but it does have some very distinctive differences. The first is that you may be able to see the roots are not restricted by depth here. There's almost as many roots at the bottom of the soil profile that we can see here, 80 odd centimetres down, as there is near the surface. And there are a mixture of grass species here. There are some thick roots and but a lot of them are quite fine. So there's no waterlogging problem here as there was in the Rensburg and indeed in the Katzspruit. This topsoil is called melanic. This is a melanic topsoil, a melanic A horizon. It has a number of features that are very, very similar to Vertic. Indeed, the two are quite closely connected. If you like to think of it this way, it's a Vertic, but not quite so extreme. It has cracks very much like the Vertic A, so that shows again that there's a lot of montmillanite clay here. But the melanic doesn't show the same ability, it doesn't show the same ability to shrink and swell. So there are no slicken sides in this particular topsoil. It doesn't shear the roots in the same way that the shrink swell of the Vertic does. And it doesn't have the same facility to self-mulch. So if we look at the roots here, you can see there's a mixture of thick grass roots, but also lots and lots and lots of small fine roots. And these fine roots can be found right down here at 80 odd centimetres, something that you would never have seen roots as fine as this in that Vertic topsoil, because in the Vertic topsoil they've got sheared off by the shrink and the swell. Another feature of the Vertic was that the roots were flattened as the soil mass moved against itself in that swelling procedure. If we look at this soil and we take a piece out of the face and just break it in half, you can see that the root is still quite circular. It hasn't been flattened at all. So despite the very heavy clay nature of this soil, it doesn't have that same facility to squash the roots. And if you look very closely, you can see the round hole that the root came out of. Again, the hole is still quite spherical. So again, there's no obvious sign here of that tremendous shrink swell that was present in the Vertic. And this is why the roots are quite happy to grow much deeper here than they were in the Vertic Rensburg. You can see in the bottom of the pit here a boulder of dolerite. So here is our soil parent material, not shale anymore, quite clearly dolerite, as indeed it was in the Rensburg profile. Dolerite, when it weathers, produces, as we've said, very clayey soils, and in an environment like this, in a climate like this, semi-arid, it produces extremely base-rich and very fertile soils. So here again, the roots were telling us that, because of the so many roots in this particular profile, and the origin of the bases is in the dolerite as it breaks down.
This soil is very fertile, quite deep and quite well drained, though clearly not as freely drained as the red soil on the opposite slope. As an agricultural soil, the Bonheim can be considered a reasonably good soil, and if irrigation were available, then can be highly productive. Under dryland cropping, potential is much lower. Bonheim soils are considered to produce sweet felt due to their base-rich nature, and can therefore be grazed for most of the year. A forester, however, will know that both melanic and vertic topsoils are characteristic of semi-arid or arid climates, as it is only under such a seasonal rainfall pattern that their typical strong structure can form, due to the clays being able to shrink and swell with changing water content. Such climates, as we've commented before, are not conducive to commercial forestry.
We've now moved down slope in the direction of that lip that I talked about in the saucer rim. In other words, we've come down the hill and we're now nearly at the outlet for the water towards the dam. And here, on this lower slope position, not far from the dam, we find an example of what happens when the soft plinthite material that we saw under the Longlands profile is exposed at the surface. When you get erosion and removal of the upper layers of the soil, that soft plinthite gets exposed at the surface, it permanently oxidizes and goes hard. And this is the material that results, called, not unsurprisingly, hard plinthite. And by hard, we mean very hard. It also goes under the name of ferricrete, which is to remind one it's related in a sense to concrete. So it has that same hard connotation. The grass here is growing in between the cracks where there's a little bit of soil still left, but essentially once this material is formed and it's hard, then very little will then grow on it. So it's very, very important therefore to protect soils which have plinthite within the profile, because if we lose the upper surfaces of the soil, the upper layers, this is the result.
In conclusion, this practical has tried to stress a number of aspects about soils, and amongst these is the fact that soils change rapidly across landscapes due to the interaction of the 5 soil-forming factors. Also, that it is impossible to consider any single soil in terms of its formation and properties without considering the surrounding soils and landscape. Soils interact with each other, and what happens upslope has repercussions downslope. All the soils that we have seen here may be considered to be young, although some are younger than others, as indicated by their features. We have also considered some of the various uses to which soils can be put. There are also some that we haven't mentioned, such as horticulture,